This is our 8th lecture. It's on something called products and co-products. And I would say that this is going to be the most interesting lecture we've had up to this point. Now, I'm not sure if Moncrief discusses co-products in the book. He definitely talks about products, and co-products are not as important in topology, but they still somehow come up. But they come up in other areas of mathematics, and they will come up later on in the semester, in the course, not in regards to topology, but in regards to group theory. So it makes sense to also talk about co-products, because they're quite easy to understand once you're familiar with products, and they will nicely fit together with the theme. And when we see it later on in the semester, and we talk about groups. And we're also going to present a modern way of looking at products and co-products. If you've noticed, the title of this course is called Modern Topology. So we want to show something done in a much more modern way. One can argue that everything up to this point has been quite classical. You can find books from like 100 years ago, maybe even more, that have discussed some of the stuff we've talked about. But today I'm going to show you something that's actually quite modern, that it really is an invention of the modern era of mathematics, where you're not going to find in older books. And it is somewhat categorical in the sense of category theory, but we're not going to talk about category theory. We're going to sort of sneak in category theory in this course without really saying what it is. So when you actually do see it one day, many of the ideas are already familiar. So it's about products, and I'm sure you all know what the Cartesian product is. The Cartesian product of two sets. We have two sets, call these sets X and Y. Then the Cartesian product, which is denoted like this, is equal to, by definition, you would say it's the set of pairs where the first coordinate comes from X and the second coordinate comes from Y. So that is the Cartesian product. It often comes up when you want to do two things together. Okay, so now what we want to talk is we want to talk about the product. So let's remove the word Cartesian, because now we're no longer with sets, and we want to talk about the product of two topological spaces. So I'll just write spaces. Product of two topological spaces. And the question that really comes up is, how do you put a topology on this? So how to topologize the Cartesian product? Because at the moment, this is just a set. There's no topology here. So when we say topologize, we want to be able to declare what it means for a subset of the Cartesian product to be open. So I'm going to show you the incorrect way to do it, and then we'll do it the correct way. So this would be the incorrect way to do it. So you can say a first attempt at topologizing the Cartesian product. And this is going to be wrong. Okay, that's not what it's going to be. So let's say O for open be a subset of the Cartesian product, and we declare that O is open if and only if it has the form that it's U times V, where U is something that's open in X and V is something that's open in Y. So you say that the open subsets of the Cartesian product are those subsets that have the form that it's some open set times some closed set. I'm sorry, some open set in U, and then Cartesian product with another open set in Y. So that's something that you would do, and this is wrong. So why is this wrong? Well, consider this example. So let us consider the real line times the real line. So this should be the plane. This should be the two-dimensional plane. So if we draw the picture of the two-dimensional plane, let's draw a picture of an open set. So an open set can be quite complicated. It can look something like this. It does not even have to be convex. It might have holes in it. So an open set might look like this. Now, how would U times V look like if U and V are open subsets of the real line? So to keep it simple, so for simplicity, let's say that U and V are open intervals, because it's easier to draw pictures like this. So if they're open intervals, then here's the way the picture is going to look like. So here is our plane. Okay, that's the two-dimensional plane. And one of these axes, you can say this axis over here, that's going to be r, right? That's like the second coordinate. And one of these axes going like this is going to be x. So this is basically x and this is y. This is sort of like x and y, but in this case, they're the same. So you have your two axes. And if it's an open subset, if these are open intervals, then you have an open interval on like the x-axis, and then you have an open interval on the y-axis. And now when you form the Cartesian product, you're going to get something that looks like this. So notice what you're getting. You're getting a rectangle. You're getting an open rectangle. So I think we can agree that if this is open and this is open, the Cartesian product of those two should be an open subset of the plane, right? That this is an open subset of the plane. However, and this is the point, the open subset of the plane also includes sets that look like this. You see that? It includes sets that look like this. They include more complicated type of sets. And so because of this, this approach is problematic. We cannot say that U is open if it has this form. So really what we should say is, the topology of x times y should include sets of this type, but also more sets. So these are not enough. You have to have more sets, because otherwise the Cartesian product of R and R will not be R2. It will not be the usual topology on R2. It would be something totally different, because if these are the only open sets that you allow. So how does one do that? So what we're going to do here is we're going to use a topological basis. So let's recall this again. So recall that often it is hard to explicitly describe every open set. So instead, we described a smaller collection of open sets, which are easier to understand, maybe to visualize, or maybe to describe, whatever word you want to use. And then an open set in general is something that contains this simplified open set as a subset. Okay, so this is how it works in metric spaces. So in a metric space, we define an open disk, and then we say a set is open if and only if at every point you can find an open disk that contains that point and sits inside your set. And in general, so that's what you do in metric spaces, but what does one do in topological spaces? So for general topological spaces, we use something called a topological basis. And I want to quickly remind what a topological basis is. So let X be a set. Okay, so for the moment we just have a set. A topological basis, let's call it B, is a collection of subsets of X. Notice I'm not saying open subsets of X, because technically X is not a topological space yet, but the idea is we're going to turn all of the sets in this collection into open sets when we form our topology. So let X be a set, and script B is a collection of subsets of X with the property, and the properties that are satisfied are this: every P in X, there is something in the basis so that the point belongs to B. Second thing is, and the other property is, if B1 and B2 are in your topological basis, then, and let's say they intersect at a point. Now, if the intersection is empty, then there's nothing to check. But if they intersect in the point, there is. Now, it could happen that the intersection is again in the basis, in which case there's nothing to check. But usually it may happen that the intersection is not in the basis. And then we're going to say there is a B3 in the basis with the point in B3, and B3 is a subset of B1 intersect B2. And then we mentioned this proposition. And then we make this definition. So let script B be a topological basis for X. And then we define, we say U, a subset of X, is open if and only if for any point in U there is something in the topological basis so that P is in B and B is contained in U. So it's very similar to metric spaces. And of course, when you see this definition, the immediate question is, does this define a topology? Because you have to check whether or not the open sets satisfy the two conditions, and that is, well, three conditions. Is the entire space, so is the empty set in there, is the entire set in there, and the entire set X, of course, is going to be open because of condition 1. But then you have other things you need to check. Namely, is the intersection of two open sets open? And the way you justify that is basically condition 2, because if you take two basis elements and you intersect them, then you can find something smaller which sits in them, and that will justify why the intersection of two open sets is also open. So the proposition, which is not difficult to prove, we never actually proved it, but it's easy to see. So the proposition says the above definition puts a topology on X. So this is a valid topology, and now X is a topological space. Okay, and maybe to add, I think I mentioned this before, but I just want to add, so any open set in X can then be written as U is a union of basis of these, and where every BI is in the topological basis. So every open set can then be written as a union of these basis elements. So for example, in a topological space, if you have an open set, you can write it as a union. Now, they might overlap, that's okay, and you might have to use an infinite number of these disks, but the point is, if you use enough of them or use an infinite number, you can write any open set as a union of those. So these are just some simple facts about bases in a topological space. So the reason why we introduce this is we will topologize the Cartesian product using a topological basis. So our basis here is going to be the collection of the following sets, where U is open in X. So U is in the topology of X, and V is in the topology of Y. And when you do that, you form a basis. So you form a topological basis. So why is this a topological basis? Well, I do not want to check every single possible condition, but let me just show you, like the most important thing you have to check is the intersection criterion. So the intersection criterion would be, what if you do U1, V1, so this is one basis element, and you intersect it with another basis element. So if you intersect them, then if they have something in common, then the first coordinate U1 and U2 must be in common, and then the second coordinate V1 and V2 need to be in common. So then these two intersect, and then this is going to be U1 intersect U2, and then times V1 intersect V2, which is again in this topological basis, because the intersection of two open sets is open, and this is open. So this is going to be in the basis. So a topological basis does not need the property that if you intersect two basis elements, the intersection is back in the basis. It does not need to, but in this case it does. And so that means we have a topological basis. Okay, and then we define, and then we define, let's say script O is an open subset of the Cartesian product. So now we're putting a topology on the Cartesian product. If and only if for any point P and O. And by the way, a point, I'm writing P, but a point itself will look like this. It will look like X comma Y, where X is in X and Y is in set Y, because this is a subset of the Cartesian product. So if you pick a point in that set, because it's a subset of the Cartesian product, it has two coordinates, where the first one is in the first set and the second one is in the other set. So I'm just writing P over here, but the P itself decomposes in such a way. So that's your point. So you would say for any point, there is a basis. So you would say there's a basis vector. So you would say that there is U open in X and V open in Y, so that the point is an element of this Cartesian product, and that Cartesian product itself is a subset of that open set, of the thing that you're saying is open. So we're not saying that an open set looks like this, but open sets must contain sets of this form. And then the open sets could be more complicated. They could be unions of lots of these. So that puts a topology on this Cartesian product. So now that we have done that, let's start discussing some theorems about the product. But I want to say something that before we look at any examples and any propositions. So what we're doing right here. So what we've done right here, all of this is very classical. This is very old-fashioned. Later, we'll show a more sophisticated version. Now, the price to pay is that it's more abstract, but it's more advantageous. You see, like the issue here, the issue with this approach is that it uses way too much set theory. So you need to think about elements, subsets, products of sets, and so on. So you have to, there's like way too much set theory going on. And sometimes when you have a large collection of objects and you start combining them together, when you start to think of them on the level of sets, things sometimes start to get rather complicated. So mathematicians have realized over the years that thinking in terms of sets and elements is often a distraction. That's not what really we care about. We more care about the properties of something as opposed to what it is on the level of sets and elements. So that's what we'll do after this. But I wanted to at least introduce this definition because they're both advantageous. Sometimes one does occasionally need to resort to this sort of very classical definition in order to prove something, but often we try to use fancier methods that we'll discuss afterwards. So this is the definition of the Cartesian product. So now this is a topological space. Let me just show you some examples. Let me start with this very easy example. Let's say maybe example 1. Let's say X is the interval from 0 to 1, and Y is the interval from 0 to 1. And of course, whenever we talk about the real numbers, it's always understood with the usual topology unless we say something else. So with the usual topology, and then if you want to visualize what this is, if you want to visualize it, now you do not have to visualize it, and sometimes one is unable to visualize it because sometimes these spaces get rather complicated and they get quite involved and quite abstract. But in this case, you can give it some kind of pictorial interpretation, and the way you do it is you think of the horizontal axis as going from 0 to 1, you think of a vertical axis as going from 0 to 1, and then you would include all of the points, and if you do that, this would be a square. But what we would say is, we would say that the product of X and Y, this is a disk, right? You say, well, why is that a disk? Well, because this is homeomorphic to a disk, right? This is a disk. So you would just say this is the closed unit disk. So obviously what we mean is, so more precisely, you would say that the closed unit disk is homeomorphic to X times Y as the product of those two topological spaces. So that's kind of what we mean by that more precisely. I mean, you can kind of see like the annoyance here. Mathematically, it's a lot more convenient to work with a disk than with a square or with a sphere, things like that. But if you think of it on the level of sets, it's not really a disk, and then you have to sort of create a homeomorphism from one to the other. But that's kind of like the issue when you when you focus way too much on the set theory as opposed to on the topology. You care more about the topology. The topology, like you describe the topology using sets and elements, but fundamentally it's more about homeomorphisms. That it's not what something looks like as a set or how the elements look like, but you can have two very different looking spaces on the level of sets, but they're homeomorphic to each other. It's the homeomorphism that's more important. So this would be, okay, so we have this. Now, let's change this up a little bit. Let's say X is S1. S1. Now, this is the circle. Now, how do you describe the circle? So here's one way to describe the circle. So one way to describe S1. Now, I say one way because you do not really want to force yourself into thinking of only one way. This is topology. Things can be homeomorphic and be different. So there's different ways to think about it. But the most common way, this is probably the most common way, is you would say S1, it's the set of complex numbers whose absolute value is equal to 1. That's the most common way. So you have your complex plane, and in the complex plane you have complex numbers whose absolute value from the origin is equal to 1, whose distance from the origin is 1. So it's the collection of complex numbers whose absolute value is 1, and this is the subspace topology of the complex plane. The complex plane has a metric, right? The absolute value is a metric. So it has a metric, so it's a metric space, and that's just the subspace of it, and that's the circle. So how to visualize S1 times 0, 1. So here's how you do it. I know that previously we draw one axis like this, one axis like this, but when we draw the circle, we're kind of going to draw it like a circle, and then we're going to have another axis going like that, and it's going to move from 0 to 1. So we kind of move from 0 to 1 on the other axis, and then we look at all of the points that we generate if we're allowed to move like this and like this. And maybe you get to see what that is. That is going to be a cylinder. That's going to be a cylinder. And a cylinder is not homeomorphic to a disk. They're not homeomorphic. Why not? Why are they not homeomorphic? Well, the simple reason for this is because we're going to discuss this later on, but the disk is simply connected. Simply connected means there's no hole, and a cylinder is not simply connected. They're connected spaces, but the cylinder has a hole. You see a big giant hole in the middle, and so they're not homeomorphic. Okay, so we have this kind of situation. So now let's do another example. Now this one's probably the most interesting one. This is example 3. That was example 2, but I kept it as example 1 by mistake. So this is going to be example 3, most interesting example. So example 3. What if we do S1 times S1? Topologically, what do we get? Now you could, of course, say that this is the set of pairs Z and W, where Z and W are complex numbers, and the norm of Z is 1, and the norm of W is 1. Of course, that is, like, fundamentally, on a very formal level, that is what that is, right? And it's not really possible to visualize it with like drawing axes or anything like that, because a complex number is sort of like A plus IB, and this is C plus ID. So then you basically have A, B, C, D, and then you have 4 dimensions, and then this is some kind of object that's living in 4 dimensions. So if you try to visualize it by just drawing like by just drawing lines, it's going to be really hard to visualize something like that. But you can be creative. So what you can do is you can go back to the previous example that we did. You can say S1 times 0, 1. So you can say that this was a circle, and then you move up 1 unit, and you get your cylinder. Now a circle is sort of like an interval where these 2 endpoints are being glued together. So like if you look at what a circle is, it's like you're taking the 2 points and you're putting them together. You're just kind of wrapping this around in a circle back to where you started. So if you think like that, then you would take your circle, and then you will make your other axis kind of go like a circle, and it will go around. So now imagine you're taking this and you're kind of moving it up, but as it moves up, it kind of returns back to itself, and maybe you can kind of get to see what that is. That's going to be a torus. That's right. That's going to be a torus. So that is actually a torus. So it's this surface that we've shown on the first day of class, but I'm sure you've seen this before in other math classes. Maybe they talk about that. You might have even seen it in like a calculus class where you parametrize surfaces. So a torus is like an interesting surface to describe a parametrization for. So that would be a torus. So now, what would this mean? So if you could somehow visualize four-dimensional space, and you were to draw that, then you would see the torus. If you're confused, how can this be if this is four-dimensional? But that's fine. This plane is two-dimensional, but this curve is one-dimensional. So you have a one-dimensional object sitting inside four-dimensional space. So this is one dimension, this is one dimension, so their product should be two dimensions. But because you have four real components, you would say that this is a two-dimensional object, but it sits in four-dimensional space. But of course, this is not possible to visualize, whereas doing this kind of interpretation, you can kind of see the torus. And what this is we would say that this is a topological torus. So a topological torus is a topological space which is homeomorphic to a torus. There are other ways to describe a torus. This is just one way. There's other ways. So we never talk about the way. There's multiple different ways, and this is just one of the ways you can describe a torus as the product of these two. In the next lecture, we'll see another way to define it. So this is the topological torus. So these are just some very easy examples. And so I want to begin with this proposition. So let's begin. I want to mention some simple propositions while we go along the way. So proposition. So if, let's say, C is a closed set in X, and K is another closed set in Y, then C times K is closed in the product space. So instead of calling it the Cartesian product, we sometimes just say the product, or sometimes we just say the product space. So in the product space. Now, of course, I want to quickly remind you, if these were open sets, then the product is open by definition. Okay, so just be very careful. Open does not mean that it looks like that. This is just something in the basis. Open means it contains something that looks like that. Okay, so let's check this. Okay, so proof. So how does one do that? Well, you take the complement. So we need to check that the complement of C times K in X times Y is an open set in X times Y. Okay, so what's the complement? So we do X times Y, and then we take away C times K. So it's a good idea to draw pictures here. Now, this is going to be almost silly, what I'm about to do. Spaces are complicated. They can look very, very complicated. But we're going to visualize X and Y as just two line segments. I mean, so you can see just how silly that is, that out of all possible topological spaces, we're going to think of X as a line, and we're going to think of Y as a line. Of course, I'm not actually saying that's how they look like. This is just a way to help you write the proof, right? You do not need the picture, but this is just a way to help you make this proof work out. So these are like the two axes, and you have some kind of set. You have some kind of set over here. You would say, oh, I'm sorry, that makes no sense. That makes no sense. It has to look like a rectangle, right? C times K has to look like a rectangle. So we have some kind of rectangle here. And that's what it is. And we want the complement. So we want all of that stuff on the outside. Now you can see that that this is sort of like the shadow on the x-axis, and this is the shadow on the y-axis. So if something is outside, then, so if you have a point that is outside, then it means the point has to either be missing from X, or it has to be missing from one of these two. So the way you would write this is that this is the complement of K, I'm sorry, it's the complement of C times Y, and then union X times the complement of K. So that's what this is. Like, what you can do this without pictures, but I think the pictures help you see this. You want the stuff, you want the stuff that's outside. So to get the stuff that's outside, let's maybe shade it in like this. If you shade it in red, and you shade this in red, and then you draw what you get, you're getting this piece, right? That's the piece that you're getting. You're getting this. So it's, oh, and also this as well. That's right, and also this as well. So you want all of that. And to get all of that, either, so the, well, I mean, I'm not sure if the picture here is the most helpful thing, but what you can say is that if something is in the complement, if it's not here, then it means that either the first coordinate is missing from K, or the second coordinate is missing. So either the first coordinate is missing from C, or the second coordinate is missing from K, and then we do not care about the other coordinate. So, like, for example, so maybe this will make it a little bit easier to see. If we're over here, let's say we have a point over here, right? So if you look at this point, notice this point, it's in Y, but it's not in X. And so this entire line is missing from the set. So if one of the points is missing from these, then either it's missing from the first one, and then we do not care what the second one is. That's why we're writing it like this. We're missing from the first one, and the second one could be anything. Because in order to be in this set, both of them have to be there. So if the first one is missing, it does not matter what the second one is. And then you kind of repeat this. And this is, of course, open, because this is open in X, because that's the complement of a closed set. This is open. And for the same reason, this is open, because X is open in itself. X is open in X. This is the complement of K, so that's open in Y. So this is a basic open set in the topological basis, so it's open by definition. And you can see it's a union of both of these. So it's a union of these two open sets. And so in the topology, it is therefore an open set by definition. Okay, so we have this very simple property that the product of two closed sets is closed. But again, not every closed set will look like that. The other thing that I want to say is we also have what are known as the projection maps. Projection maps. So we have X times Y, and we have a map going, this is the projection onto X. We write it like this. Now, here's how you know you are an advanced math student. Because when you first learn pi, you say it's a number. It's some kind of number or whatever it is. But then when you get much further into mathematics, pi almost never means the number pi, and it starts to mean that it's like the projection map. You can also call this p if you want to, if you do not want to use Greek, but we obviously call it pi for projection. So this is the projection map onto X, and this is the mapping which is defined in the obvious way. So if you have a point in the Cartesian product, then you just drop off the Y coordinate and you keep the X coordinate, and then you have the projection map onto the other coordinate. There's two of them. So the projection of a point would just be equal to Y. So this is sort of the obvious maps. And it's a very easy proposition, which I'm going to leave as an exercise. And what you show is you're going to show pi X and pi Y are continuous maps between topological spaces. They're continuous maps between these two topological spaces. So X is a topological space, so is Y, and then you topologize the Cartesian product with the product topology, and pi X and pi Y are continuous maps. This is very easy to show. You just have to go back to the definition of what it means to be a continuous map. By definition, that is when the pullback of an open set is an open set. So you just have to do that, and you'll be able to see that these are indeed continuous maps. The next thing that I should say about this, there's a follow-up proposition. So this is the follow-up proposition that pi x and pi y are open maps. So what's an open map? So an open map is quite simply, in other words, pi x and pi y map closed sets. I'm sorry, open sets to open sets. If you prefer to say, you can say that the push forward of an open set is open. Okay, so if you recall, we made a warning, a very big warning. We've said that continuous maps, by definition, they pull back open sets to open sets, always. That's just the definition of being continuous. However, continuous maps, they could, but they do not have to, push open sets to open sets. And in the case of these projection maps, they do. Projection maps, they push open sets to open sets. Now, I want to give you a warning over here, very big warning. You might think that since continuous maps pull closed sets to closed sets, that an open map also pushes closed sets to closed sets. I mean, I can understand why someone would think that, because the definition of a continuous mapping is you pull open to open, and then you can show by using complements that you also pull closed to closed. Okay, so you would think that maybe an open mapping, since it pushes open to open, maybe by using complements or something, it pushes closed to closed. That does not work. That is not a thing. There is no such thing. There is no such thing. Does not need to be true. I mean, I guess it could be true. Does not need to be true. You can come up with examples when it's true, but we of course are asking if it's true in general. And I want to give you an example. I'm going to prove to you this proposition after the example, just so we get to practice the product topology. But here's like a super easy example. So in this example, you always want to think of the easiest possible examples. Just take the real line, take the real line. So the product is the plane. And then we have, this is sort of the x-axis, which I'm going to draw as r. Then we have this axis, which is going to be the y-axis. And let's draw a hyperbola, like a piece of, so this is asymptotic. So this is a hyperbola. I know you're going to tell me a hyperbola has a second half to it. It does, but in this example, we do not really care. This is a hyperbola. This is a closed hyperbola, a closed set, r times r. Why is it a closed set? You just go back to the definition of closed. You look at the complement, and you see if it's open. So the complement of the hyperbola, if you pick a point not on the hyperbola, let's say right over here, can you draw an open set which is contained in the complement? Yes. Right? This open set is contained in the complement. So the hyperbola, you can see, I know it's not a formal proof, but I think it's believable enough. The hyperbola is a closed set in r times r. Now look what happens when you project, when you drop the shadow down to the r-axis. When you drop the shadow, right, when you drop the shadow down, what do we get? We get all of this, right? We get all of this, and then this is not being included because it's asymptotic to it. Now look at this set. I think you can agree by looking at this set that this is not a closed subset of the real line anymore. It's an open subset of the real line. And I know I told you that open and closed are not opposite concepts, but in this case they're opposite concepts because, well, they're not opposite concepts, but you cannot be open and closed at the same time as a subset of the real line because the real line is connected. So other than the trivial examples, there's no clopin sets. But you can also just see that this is not closed because its complement is not open. So so this is not open. I'm sorry, this is not a closed subset of the real line. So you started with something that was closed, you took its projection, and its projection is no longer closed. So you do want to be very careful with this. These projection maps are open maps, but they're not closed maps. So I think maybe what we should do is we should prove that they are indeed open maps. Let's see how the proof goes. So let's take all of this away, kind of gets in the way. Focus on the proof. So proof. So like without loss of generality, we can assume that O, which is our open subset of the Cartesian product, is a basic open set. So I leave that up to you. So O is of the form U times V, where U is something that's open in X, and V is something that's open in Y. Okay? And let us show that pi X, so this is the projection onto X, is an open map. So we want to prove this is an open map, so we have to pick an open set. We have to pick an open set in the product space. So we pick an open set in the product space, and we can assume that that open set is a basic open set. Why is it? I'll tell you the reason afterwards. I just do not want to interrupt the flow of the proof. So you pick an open basic set. So here's O, it's this. And you want to show, we want to show that pi X U times V, right? This is you're pushing the open set forward. Pi X of U times V. You want to show that this is open, right? You want to show that this is open, but what's the projection? Well, you're just projecting onto the first coordinate, right? This is the first coordinate. That's just equal to U. In fact, I think the picture makes this very easy. If this is X and this is Y, and your basic open set is this rectangle, then when you project it down, you're getting this. So if it's of the form U times V, then you're just getting U, which is open in X, and then the proof is complete. So I guess that took almost no work. So I guess then it's actually important. It's actually therefore important. So maybe I'm going to remove this. This is not obvious. So sorry about that. So maybe I should say, let us first assume that O can be written, that O is a basic open set. So it's true for basic open sets, but why is it true for open sets in general? So if O is open in general, then O can be written as a union of basic open sets. It's some collection of basic open sets where these are of the form Ui times Vi. So an open set is therefore a union of these basic open sets. So then if you apply pi X to O, this would be pi X of this union. And now we reach one of these questionable parts. Is the push forward of a union is the union of the push forwards? And this is like one of those things that one can always forget. Like, is it supposed to go like this? Is it supposed to go like this? Is it equal to? And in this case, it's equal to. So this equality, the equality is justified since pi X is a surjective map. So when your map is surjective, then things work better. So pi is the mapping from x times y into x. Is it true that every element of x comes from somewhere? Of course. Pick any element, and then you have x times whatever, right? y0. Just pick any fixed y0, and that gets mapped to x. So this is, of course, a surjective map. And when it's a surjective map, then there's less risk associated with interchanging the union with the push forward. You can kind of interchange them. And we said on the previous line that these are open. Those are open because when you apply the push forward to a basic open set, it's going to be open, and then you have a union of open sets. So this is going to be open. That's an arbitrary union, but an arbitrary union of open sets is going to be open. So that means that whatever that is, that's therefore an open set. And that justifies the fact that you have an open mapping. Okay, so that completes that proof. Now moving on to the next thing. Let's maybe say something about Hausdorff spaces. So proposition, and I'll make this an exercise. The product of Hausdorff spaces is Hausdorff. While I'm writing this, I think I see a very elegant way of proving this. But I do not want to try to attempt to write the proof right now, because sometimes you realize that it's longer than it is. So maybe I'll just put it, I'll try to work it out, and then I'll put it on the next assignment. When I mean a more elegant proof, I mean avoiding the use of set theory. We try not to use set theory. It's a little bit annoying. You can, of course, now the way you can prove this, and this is the way you're intended to prove this, is you take two Hausdorff spaces. So Hausdorff just means that points can be separated by open sets. So you take two Hausdorff spaces, you pick a point in one of them, you pick a different point, and then you show by using like basic open sets and some kind of form that they have that you can find subsets that contain those elements from those sets in a certain way and they do not overlap. That's what I mean by like a set theory type of a proof. But I think there's like a more elegant way to prove it by using mapping properties. So this is kind of interesting. So this is like just an interesting, idea. So X is Hausdorff if and only if the following set, where X is an X, is closed in the Cartesian product. So this set, it's called the diagonal. So that's the name of that set. You can see why it's called a diagonal, because if you think of this as X and you think of this as X, then this is the set of points where both of them are the same. So it would kind of go like this, right? That would be the diagonal. So there's this theorem about Hausdorff spaces that something is Hausdorff if and only if the diagonal is closed. And I think if you use that fact, there might be a fancy way of proving this, but I do not want to go there. Probably what would make more sense is to put this on the homework, and then you think about it, see if you could make a more elegant kind of a proof. So that's the proposition. The product of two Hausdorff spaces is Hausdorff. And then we have something similar with connected spaces. So let's say that the product, so proposition, the product of two connected spaces is connected. So this one is actually harder to prove. Moncrief puts in some work in showing it. It's not too hard. But I want to show you an interesting proof. So this is sort of like a clever proof. So this is a very, very clever proof. This is not something that comes to mind. Because usually, how do you show that something's connected? You show that the only clopen sets are the trivial ones. So basically, you want to show that X is connected, Y is connected. You want to show the product is connected. So you pick a subset of that, of the product, and then you assume that subset is open and closed at the same time, and then you argue that that will therefore imply that that they're connected. That the subset that you have, the only way it could be open and closed at the same time if it's like the entire space or the empty set, kind of do that. So that's the more straightforward way of doing it when you're using the propositions. But there is a elegant way of doing it. I'm going to actually show you. I think I have another way of doing it. I just realized right now. I think there's another way to do it, but you have to assume something extra. So I'm going to first show you the clever way of doing it, and then I'm going to show you an additional way to do it afterwards. So I think there's another way to do it. So it's just that I'm being a little bit distracted right now, because while I'm trying to write this down, I'm kind of thinking about the different ways you can prove it in the middle of that. So it's a little bit hard to focus on what I'm trying to say. But let's discuss this clever way. So this is the clever way. So it's based on this idea that if Z, so let's call it Z. If Z is a disconnected space, then it is possible to find a continuous map, let's call it F, from Z into the set 0, 1. Now the set 0 and 1 is given the discrete topology. So everything is an open subset of this. So you give it the discrete topology. You can find a continuous map. Now what's the idea? The idea is basically this. The set Z is disconnected. So here's a picture of it. Because the set is disconnected, so this is Z, there's one piece, and then there's another piece. There might be more pieces, but then it does not really matter. So you have two pieces, they're disconnected, and then you define the following function on Z. If you pick a point in Z, if it's in, so you're just going to look in which of the two pieces it's located in. So if Z is, if you have a point in this piece, you can set it equal to 0, and if you have a point in the other piece, you set it equal to 1. Okay, so if Z is disconnected, then you can find a continuous map. So this subset of Z is mapped to Z. Every point is mapped to 0, and every point in here is mapped to 1. And then this is going to be a continuous map. And to generalize this, if Z is disconnected with K components, so recall we talk about the components of a set. The components are the maximal connected subsets. So if your set Z has a finite number of components, actually it can have an infinite number of components, but I do not want to go there. So let's say it has 4 components, then you can map this one to 1, 2, 3, 4, or whatever labels you want to choose. And then you can have a function that maps Z into, let's say, 1, 2, 3, up to K, where you just assign it the value of which component you're located on. And this is going to be a continuous function. So why is this function continuous? So the reason why this function is continuous is it has something to do with what you did on the homework. Because Z can be written as, let's say, Z1 union Z2. And Z1 and Z2 are clopin. So this is, they are disjoint. This is open, and its complement, which is Z2, is also open. So you're going to define one function, let's call it F1, and it's a function from Z1 into 0, 1, and this is the function that maps every point to yeah, so let's call this function F0. So let me write like this, let me call the components 0 and 1. This is F0, so this function maps everything to 0, and this function maps everything to, so this would be 1. This one maps everything to 1. Okay, so these are continuous. So these are continuous since they are constant maps. Constant maps. Constant maps are always continuous, because if you pick an open subset of that, if the subset does not contain 0, it's empty. I'm sorry, yeah, it's empty, which is automatically an open subset. If it contains 0, then the pullback is Z0, which is Z0, which is an open subset of Z. So these are going to be automatically continuous map. Constant maps are always going to be continuous. So, and then you put them together, and then you define a mapping from Z into 0, 1 by just sort of gluing the two maps together. You say F of P is F0 of P or F1 of P, depending on whether the point belongs to Z0 or Z1. And you had an exercise on the homework that if a set can be written as a union of open sets, and the functions, when you restrict them to each of the open sets, is continuous, then that would mean that that the glued function, the entire function that's defined on the union, will also be continuous. So this is what you call gluing continuous functions together. Okay, so that's the idea. So if Z is disconnected, then it's possible to find a continuous map that will do this for you. By the way, if the space is connected, then it's impossible to do this, because the push forward of a connected set is connected. And since this is a discrete space, it either has to be 0, 1. I forgot to say one very important part. So if Z is disconnected space, then it's possible to find a continuous map which is not constant. Of course, that's what I meant. Which is not constant. That's the key point, where it's not constant. You can, of course, do that. You can always map everything to 0, but you do not want it to be constant. So I just want to say this again. If Z is connected, if Z is a connected set, then the push forward of Z, the image of Z, has to be a connected subset. Now, because this is a discrete space, the push forward will either have to be 0 or 1. So if Z is a connected space, then this is impossible to do. Okay? So here's the idea. So to show that, let's call Z is equal to X times Y is connected, we will argue that it is impossible. Well, I'll say it a little bit differently. We will argue that if f is a function from Z into 0, 1 is continuous, then it must be constant. So it either maps everything to 0 or it maps everything to 1. So it's like a very interesting way of thinking about connectedness. You can interpret connectedness on the level of mappings. And the number of components tells you how big you could make your discrete space. So how do we do this? So pick a point in Z. So I'm going to write this point P comma Q in Z. Z is X times Y, where P is in X and Q is in Y. Okay, so here would be very helpful to have this picture in mind. So I'm going to draw a picture down here. So we have this is X, this is Y, and we have a point P comma Q. So here's our point, and then we're going to argue from there. Now, so observe that, let's say, this P times Y, which in this picture represents this entire line. I kind of missed the point. So this is the singleton. This is the singleton set P times Y. So the first coordinate. So this is just another way of saying the first coordinate has to be P, and the second coordinate could be anything. So in the picture, it's this. So whatever this space is, that this space is homeomorphic to Y. Okay, this space, right? This is a space. So this is a subspace. This is a subspace of the product space, right? This is actually a closed subset because, well, actually, I want to be very careful. A single point is not necessarily closed. Just be a little bit careful. But it does not need to be a closed subspace. The point is, this is a subspace of the product space, and the subspace is homeomorphic with Y. And the mapping here is obvious, right? You take P comma Y and you map it to just Y, and it's an easy exercise to prove. It's clear that this is a bijection, and you just have to show it's a homeomorphism. So I leave that up to you, right? If you look at it visually, it just looks like a copy of Y. So as a set, this is different from that, but topologically speaking, they are the same thing. And what do we know about Y? Y is connected. So because of the homeomorphism, this is connected. So if we restrict if we restrict this function from the product space to this connected subspace P times Y, it is continuous, right? Because if you restrict a continuous function to a subspace, as we said in class and you had on the homework, it's going to be continuous. Restricting the domain, restricting the codomain, extending the codomain, the continuity will be preserved. So it's going to be a continuous function. So f, when restricted to this line, to the line P times Y, must be constant. It must be constant on that line because that's a connected space. So without loss of generality, say that f is equal to 0. So we're going to therefore assume that the function, this continuous function when restricted on this entire line, is equal to 0. So on this entire line, the function is equal to 0. Okay, so by the same argument, okay, so now pick any point. Let's say, now pick any point, let's say y in Y, and consider the line, let's say x times y, like this. Okay, so now you're going to draw another line. So you're going to pick some y somewhere, right? You're going to pick some y over here, and you're going to form this line again. Great. So when f is restricted to this line, it is constant. So it's either equal to 0 or 1. Now, which constant is it? But x cross y, I'm sorry, x cross singleton y, and the other line, P cross y, intersect. They intersect at, where do they intersect? They intersect at P comma y, right? That's something common to both of them. They clearly have an intersection point. You can see in the picture they intersect, but I wanted to actually write it out because the picture could be deceiving. So they intersect somewhere. So this is some constant. It's either 0 or 1. But then this is another constant, but which said it has to be 0. So it has to be 0 on this line as well, right? They intersect, so it has to be the same. So the constant value of f on this line is also equal to 0. Now, if we vary the line x times y by moving y throughout the entire space, we fill out the entire space, and f is equal to 0 on that entire space. So you can see in the picture, you can do this with a different line, right? You can do it with this line, and on that line, it's equal to 0. And then you can do it with this line. You can do it with this line. It's equal to 0. And then you can just keep on doing it. You can just keep on filling it out. And when you stack them together, that gives you the entire space. So that's a really, really nice proof. That's a very nice proof. I really like this proof because we're minimizing set theory. So if you kind of look back at this proof, we're saying very little about the product topology. Very, very little about it. Because if you wanted, like, if you were to do it the way you would think to do it, where you're kind of working with clopin sets and then you're showing they're both open and closed and all of that kind of stuff, and you have to go back to the way the topology is defined, you can do that. That's not exactly the most exciting thing to do, and I think this is a much nicer proof. So the space has to be connected. I'm going to show you another way how you can write the proof that's going to work. Now, the next thing that I want to move to is, so we've said that a product of two Hausdorff spaces is Hausdorff, and we've said that a product of two connected spaces is connected. what about a product of two compact spaces? A product of two compact spaces. So this is the question. So then this is the proposition. The proposition says that if X and Y are compact spaces, then their Cartesian product is also compact. And this is actually a lot harder. It's not too hard, but it's a longer proof. You can see it done in Moncrief if you want to see it, and it's done in a more straightforward kind of a way. So he uses, I just briefly looked at his proof, and he basically just goes back to the topology and how it is defined, and then he basically shows it by definition. He shows that if you have an open covering of this, and the open sets could be more complicated than the basic sets, and then from there he kind of argues that if you have an open covering, from that open covering you can get a finite subcovering, and I think somewhere in the process he has to use some kind of lemma. I think he calls it the tube lemma, like the tubular lemma along the way in order to make this work out. So you can of course do that, and it's a longer proof. The most important thing is just to know this fact, but I want to show you a nicer way to do it. And I was thinking, when I was preparing the notes for this class, I was thinking about doing it the following way. And at first I thought the proof was working out, and then I noticed a mistake. So I'm going to call this fake proof. This is going to be a fake proof. And you're going to try to see what the mistake is. And then we're going to see how we can fix the mistake. So unfortunately, I mean, this is going to be a somewhat nice proof. It's not too complicated. But unfortunately, there's going to be a flaw somewhere in the proof. And while I'm writing the proof, see if you can spot what the flaw is, and then we can discuss how to fix it. Okay, so fake proof. So here's how it goes. So let us use the closed version of compactness. So if you recall, we mentioned two definitions that are equivalent to how to define a compact space. So one of those definitions involved open sets. It said that if we have a space and it's a union of a collection of open sets, then a finite number of those open sets are sufficient to cover the space, to write it as a union of those open sets. And then we had the closed version. The closed version is the one where we had closed sets. And the closed version said that if we have a collection of closed sets, and the closed subsets, if you take a finite number of them, and they intersect in something that's non-empty, then if you were to take the intersection of all of them, they will intersect into something that's non-empty. So that was the version of compactness that we had. And if you've noticed, I've actually emphasized the closed version of compactness quite a lot in this course, because I think it's something that does not get enough treatment. I've noticed that almost everyone exclusively always works with the open covering version, as opposed to the closed intersection version. But sometimes you might have noticed that the closed intersection version works a lot better. It's like a lot easier to use. So, and when we presented a proof for the Heine-Borel theorem for the unit interval, we've done it using closed sets, something that no one else seems to do. But I wanted to just overly emphasize that you can use the closed version, and you should be comfortable using that version, because I know that when you look it up in Moncrief and in other sources, they will almost exclusively do it with open sets. So you'll get to see plenty of versions like that. And I just thought, for the sake of variety, that it would probably be beneficial to do it with closed sets. I'm going to use the closed version again. So let's do it like this. So let's use the closed version. So let Ci be a collection, or a sequence if you want, is a collection of closed subsets of the product. And we're going to suppose that if you choose a finite number of them, that the intersection is non-empty for any finite subset. So if you choose a finite collection of indices, so this is a subset of I is the indexing set. So if you choose a finite collection of indices, and the intersection of all of them is not empty, then we want to show, so the goal is to show goal is to show that the intersection of all of these is also non-empty. I'm sorry, is also non-empty. Okay, so here's the way we do it. So we're going to map these. So we're going to use the projection maps. So this is the projection map onto X, and then we're going to do something similar with the other projection maps. So we're going to use the projection maps, and this is what we're going to say. We're going to say that since CI1 intersects CI2, CIN is not empty. It means if you apply the projection map onto X, see, and when you apply the projection map, I actually think that when it's intersections, the push forward of the intersection is the intersection of the push forward always. It does not even matter if the map is surjective or not, but in this case, it's certainly fine. So you're going to take the push forward, and you're going to get CI1 intersect pi x CI2 pi x CIN. This is non-empty. Okay, so it means this is non-empty. So what's the implication? So thus, the collection of closed sets pi x Ci I in I also satisfies the finite intersection property. Finite intersection property. So there is a point P. It satisfies the finite intersection property, and we are assuming that X is compact. Right? This is where we're assuming that X is compact. So we have these closed sets. They satisfy the finite intersection property, and so by compactness, so the intersection, if you were to take the intersection of all of them, this would be non-empty. So there is a point, let's call X in set X, where X is an element Ix Ci for all I in I. Okay, so we have this. Okay, and now repeating the argument with Y, because this is also compact. We're assuming both X and Y are compact. We can find the Y in set Y so that the property is satisfied, where Y belongs to all of the projections onto Y for all I in set I. But then this pair X comma Y would belong to Ci for all I in I, because look at what happens. X, so the projection onto X means the first coordinate. X is always a first coordinate of all of these closed sets Ci, and Y is always a second coordinate of these sets. So then X and Y taken together as a pair would be an element of Ci for all I. And what does that show? That shows that the intersection is non-empty, because you can find the point that belongs to all of them. That's a fairly nice proof. It's also nice because you get to see that using the closed version somehow makes it go very smoothly, but there is a flaw in this proof. And maybe you notice what the flaw is. The flaw is that this is not necessarily closed sets anymore. They're not necessarily closed sets, because the projection maps do not need to be closed. So unfortunately, this proof falls apart. So this proof would be okay. So when would this proof be okay? So this proof is okay. We somehow knew that the projection maps were closed maps. And maybe there is a special case when they are closed maps. Maybe there's some kind of special case. And that's actually what we're going to do. We're going to prove this compactness theorem in a special case, which might be a little bit controversial. You might say, well, you're not proving it in general, but as you're going to see, this special case is general enough for the things that we want to do. And so I think it's perfectly okay. So when can you do this? So here is, I'm going to take this down, and I'm going to discuss with you a case when the projection maps are closed maps, and then this proof is okay. And then we would have this theorem with an additional hypothesis. This additional hypothesis is not actually necessary, but it's going to be harder. So I'll actually tell you what the hypothesis is. So the additional hypothesis is that the spaces are Hausdorff. That's the additional hypothesis. So if you add the Hausdorff condition, then it will turn out that these are closed maps and everything goes through. And as I indicated earlier, in this course, we're going to almost exclusively work with Hausdorff spaces once we get through the point set topology. Not everything in mathematics is a Hausdorff space. The one exception is, the main exception is in algebraic geometry. But in algebraic geometry, you do not use this. In algebraic geometry, you use something else. You're not using that. You're doing something totally different. So it's just interesting that we talk about this more general proof of this fact, but it often does not come up from what I've seen. So in most cases, you work with either Hausdorff spaces, or you're in the algebraic geometry world, and then you're doing something unrelated to this. Like you're not using this. You're actually using these things called complete varieties or complete schemes, and you're doing something similar to compactness, but everything's like set up in a very different way and defined in a very different way, in a more abstract kind of a way. So you're not even returned back to that. So because of this, I'm going to tell you this proposition. So the proposition here is going to be this. So here's the proposition. If x and y are compact and Hausdorff, then the projection maps are closed maps. They push closed sets to closed sets. So they're going to be closed maps. I'm going to show you a fake proof again, and I'll show you the correct proof. So here's the fake proof. Well, actually, I would say this is a circular proof, which also makes it fair. Circular proof. So you would say that since x times y is compact and Hausdorff. So let me say it like this. We know x times y is compact and Hausdorff. We know it's Hausdorff because a product of two Hausdorff spaces is Hausdorff, and it's compact by the previous proposition. But the reason why this is circular is because the previous proposition that we proved assumed that it's Hausdorff. So if you're willing to accept that the product is Hausdorff, then that the product is compact, then here's the way the proof goes. So you say that if C is a closed subset of x times y, then C is compact. Because a closed subset of a compact space is compact. So the product is compact. So C is compact. So so if you pick a closed set in the product, it's going to be compact. So then the projection onto X is compact subset of X. It's a compact subset of X because our theorem on compactness says that continuous maps, they push compact sets to compact sets. So that's a compact subset of X. But X is Hausdorff. And all compact subsets of X are automatically closed. So pi x of C is closed. So we've proven that it's a closed map, and then you can do the exact same argument with the other one. So they're both closed maps. But this is a circular proof. So we have to give a non-circular proof. But I think this is kind of interesting to just recall a lot of the theorems. I kind of just intentionally put it in here because I wanted to go over a lot of the important ideas that we talked about in the previous lecture. I thought this would be a good opportunity. So let's therefore talk about the correct way of proving this. So it's a somewhat interesting of a proof. So here's the way it goes. So let C be a closed subset of x times y, we will show that pi x of c is closed in x. And the other one, pi y of c, it's the exact same proof, just repeated all over again. Okay, so what do we do next? Okay, so here's what we do next. So by definition, we will show that if you take the complement, that this is open. And how do we do that? We're going to pick a point in this set, we pick a point in the complement, right? We pick a point in the complement, which is another way of saying we pick something that's not in C, right? We pick something that's not in C. If there is nothing in C, then there's nothing to prove, because then this projection is all of X, which is automatically closed. So let me just show you a picture here. This is X, this is Y. If you have a closed set that kind of looks like this, let's say, right? This is your closed set. When you project it, it's everything. And if it's everything, you win. So the more important case is when, let's say, it goes something like this, and you project it, it's not everything. So there's some point, P, which is not in the projection. Okay, so this is the projection of this closed set. You have something in P which is not, so this is a closed set. We want to prove this is closed. So the idea is we're going to pick a point, and then we're going to try to find an open set that contains it, but does not intersect. Right? We want to find an open set that contains it but does not intersect. That's by definition of what it means to be open. Okay, so so what do we do next? Okay, so then the line, so we kind of do a very similar kind of a trick. We look at the line, so singleton set P times Y does not intersect. So it does not intersect. So I made, it does not intersect C. Right, you draw this line, you can see the line does not intersect this set. Okay, now here's the thing. Since P times Y is compact, so this is where we use compactness. Why is it compact? Because it's homeomorphic to Y, is compact subset of X times Y, and C is a closed subset of X times Y. So the line is a compact subset, and C is a closed subset. And X times Y is Hausdorff. Thus, this was a homework problem on the previous assignment. We can separate these two sets by open sets. So in the picture, we can find some kind of open set U over here, and we can find some kind of open set V over here that contain them, but do not overlap. So we can find we can find U and V. These are open in the product, so that U contains C, V contains the line, and U intersect V is empty. But then look at this. If you take V and you project it down, you get something open, because projection is an open map. But then the projection of V onto X contains P, and it does not intersect. Right? It contains P. This is an open set, right? So we found an open set. It contains P, and its intersection with the projection of this closed set is empty. Right? You can see from the picture that the projection down here and this. I know I'm drawing pictures, but all of this can carefully be verified from just using sets and just carefully thinking this through formally. But I think the pictures are just more instructive. So it's a very, very proof, I think. It's a very nice proof because at some point you have to separate sets. So it's nice. It's nice to see how everything gets used like that. Okay, so if these are compact, so if X and Y compact and Hausdorff, then they're closed maps, and that means that the proof of the product theorem for compact spaces, it's correct. So now I want to actually say one more thing before we talk about something that's modern, and it's this. So we can now complete the proof of the Heine-Borel theorem. Okay, so what does the Heine-Borel theorem say? Heine-Borel says that A is a subset of N is compact if and only if it is closed and bounded. So here's what we did. We proved that it has to be closed. It has to be closed because a compact subset of a Hausdorff space is closed. This is a Hausdorff space. We proved that. On the homework, you proved that if it's compact, it has to be bounded. That's actually the easiest part. So you did this one, you did this one. Now, what about in the other direction? So we have shown that 0, 1 is compact. So we gave an outline of the proof in class, and then you had like a more carefully written out proof on the homework. So 0, 1 is compact. So A comma B is compact. So any closed interval is compact because they're homeomorphic. There's a homeomorphism between them. And now you get to use the product theorem. So you have A1, B1 times A2, B2. And if you can take the product of two spaces, you can take the product of three spaces. So if you have X times Y times Z, the way you can interpret that is you take the product of these two, and then you take the product of those two. And if you have a product of 4 spaces, then you have times W. So you just take a product 2 at a time. So if all of these are compact, this is compact, then because this is compact times Z, that is compact. Since these 3 are compact, so since all of that is compact, this times W is compact. So they're all going to be compact. So you can kind of keep on multiplying them out like this. So these are going to be, so this is compact, right? So this is a compact subset of Rn. That's a compact subset of Rn. So that's a closed rectangle. Or you can say a box, depending on how many dimensions you want to visualize. So this is a closed rectangle. And the reason why it works is because this is a Hausdorff space. So we proved the compactness theorem when you have a Hausdorff space. And this special case applies here, so the proof goes through. So this is therefore a compact subset of Rn. And now here's the idea. The idea here is very simple. If C is closed and bounded, so let's say C is closed. Let's say is bounded subset of Rn, then C is a subset of this rectangle. You can make all of these numbers big enough so that C fits inside a closed rectangle because it's bounded. It does not go out to infinity. It could be a very complicated set, but you can always enclose it in a closed rectangle. Now, C is closed, and this is closed as a subset of Rn. So I should say that C is closed as a subset of Rn, and this is closed as a subset of Rn. So therefore, C is closed as a subset of this product, okay? Because the closed subset of a closed subset is closed in the larger space. It's the same thing with open sets. An open in an open is open in the larger space. So therefore, this is a closed subset of this. And this entire thing is compact. So that means that C has to be compact also, because it's a closed subset of a compact space. And just like that, in just a few lines, we managed to prove the Heine-Borel theorem in pieces, but somehow all of these pieces, they come together, and the final grand conclusion is the Heine-Borel theorem. So this is sort of a simplified way to prove it if you take advantage of a lot of these facts from topology. And I want to move on to something else. I want to discuss, so let us discuss a product space in a more abstract way. Okay, so I want to begin with this proposition. Okay, I'm going to be, well, maybe I should, yeah, I want to begin with this definition. So I'm going to begin with this definition. Let X and Y be two spaces. So these are topological spaces. The product space is a space called a space P for the product space, such that we have two continuous maps. Let's call them pi x from P to X and pi y from P to Y, which are optimal, or the actual terminology is called universal, but I want to emphasize the word optimal, are universal in the following sense. And it's in this sense. So if Z is any other space with continuous maps, so it does not matter what you call them. Let's call them F and G, with continuous maps F and G. Then there is a unique continuous map. Let's call this unique continuous map, for lack of a better name, let's call it H, from Z to P, such that, so I'm going to draw a picture for what's going on. You always want to have a picture here because it's very easy to forget. So here we have X, here we have Y. The product space, in the product space you have two projection maps, pi X and pi Y. And so I'm saying it's optimal, it's the best such case. And you want to think of the supremum from advanced calculus. The supremum is sort of like the optimal upper bound. It's the least upper bound. It's an upper bound, and it's the smallest such upper bound. That's kind of like the picture you want to keep in mind. That's the analogy, sort of like the supremum. It's the optimal upper bound. So it's like you have X and Y. I'm not saying it's like an upper bound. Like, I mean, these are not numbers, but I'm just saying it's like an analogy. It's an analogy. It's a way to help you think. P, think of P as being like larger than these two numbers, if they're numbers or something. So P is larger than these two, and it's like the supremum. It's the least upper bound. So anything else which is bigger than these two, so what we're saying is, let's suppose there's another space, Z, that projects to these two. There's another space. Then in such a situation, there is a unique continuous map from Z to P. So it's like least upper bound. Anything bigger than an upper, anything else that's an upper bound has to be bigger than P. So it kind of goes back down. So there has to be a map going this way, which you call H. And it makes the diagram commute such that, so when you do the compositions, you get this. So this one, which is what we're calling F, such that F, the red one, is this composition. It's pi X composed with H, and G is pi Y composed with G. So let me see if I did that correctly. So if you go H first and then you go pi X, you get this red arrow. And if you go H first and you go pi Y, then you're supposed to get that one. So this is the abstract definition. Okay, so this is the abstract definition of the product space. You are saying it's abstract because you're not saying what P is as a set. You see that? You're not saying what it is as a set. You're saying what it is through some mapping property. It's the mapping property that you're emphasizing. You're not emphasizing what the space is as a set. That's what makes this very sophisticated, because usually when we think of mathematical objects, we're thinking of mathematical objects as like a collection of sets and elements, and that's usually how we work with it, but it's more convenient to work with properties. So if you've noticed, in many of the proofs that we were doing using the product space, We were trying to sort of deliberately avoid using as much set theory as possible, and we try to often use those projection maps to make things work out. So the abstract definition sort of just completely ignores how the product is defined, and it just jumps to the kind of property that it has. So this is like the definition that it satisfies. And what I'm going to show you, this is what I want to show you, is I want to kind of tell you two things about this. So I'm going to take this down. Maybe I should have not taken that down, but that's okay. So what I want to show you is this. So if you can make this definition, but how do you know this thing exists? So the proposition here is that the product space exists and is unique. So unique in the topological sense. So unique in a topological sense. So any other space that satisfies these mapping properties, so it's sort of like the supremum of X and Y. Any other space which satisfies these kinds of mapping properties will have to be homeomorphic to it. And then we do not have to think of P as a set or anything like that. So why does the product space exist? So the reason why the product space exists, well, that's what we were saying earlier. So the work that we did before is sort of the existence of that. So we have X, so we have X, Y, we have the product, the Cartesian product, which we've topologized, and we have two projection maps. So let's show why this thing exists. So let's say we have a Z. Okay, so we're claiming that the Cartesian product that we've topologized in the way that we did satisfies the required property, that this is indeed a product space. So what do we have to show? We have to show that if you have Z and you have a mapping onto X, it does not have to be onto X, I should say into X, and another mapping into Y, then we want to create a mapping from Z to that product that will make this diagram commute, so that if you follow the arrows, then they agree with each other. So how does one do this? So let's say you pick an element. So you pick an element in Z. So let's give it a name. So let's call that P. So you pick an element in Z, and you have to be able to define where P goes to, right? You're trying to define. So the question is, so we're trying to show how this H is being created, and furthermore, that it can only be done in a unique way. So let's see what happens with Z. So we have this blue arrow, F, is going to take that point and is going to send that point to F of P. Okay, so F applied to P, that's F of P. So F of P is going to be an element of X, and G is going to take P and it's going to send it to G of P. So this is going to be G of P. So we have it right there. So we have F of P, we have G of P, and then what is therefore the correct element in here? So what's the correct element? So we have this projection map, right? That we have this projection map, and it has to go to F of P. So the correct element in X, the first coordinate has to be F of P, and the second coordinate has to be G of P. So H is defined as follows. So H will go from Z to the product, and H of a point would be F of P comma G of P. So it's clearly there's a unique way to do this. So clearly this is the only way to do this. To do this. It's the only way to do that because it's forced. Everything is forced. If you follow through by F, you get F of P. If you follow through with G, you get G of P. So if you want, so whatever this point is, if you want that point to descend upon F of P, the first coordinate has to be F of P, and the second coordinate has to be G of P. So this mapping H is forced on us, and it has to be equal to this. Okay, so it's forced. So it exists, and so it exists, right? It exists. That's how it's defined, and it is unique. There's only one way to do it. So we just have to check why it is continuous. So why is it continuous? So is it really continuous? Right? And then if it's continuous, then that would be the end of the justification why such a unique map has to exist. So is it really continuous? So here's the way you do it. So you just have to check the open set condition. So you have to pick an open set in here and see where it goes, right? You have to pick an open set. So you have to pull back an open set. So so let's say you can assume it's a basic open set. So you pick a basic open set of the form U times V, and the question is H inverse of U times V open in Z? That's the question. Is that open in Z? So that's what we have to check to see if it's continuous. Well, so here's what happens. When you pull back that open set, the way H is defined, this coordinate goes to f of p, and so basically I think it's just better for me to write it out. This is equal to f inverse of u intersect g inverse of v. That's what it's equal to. That's what it has to be equal to, because the way this map H is defined, it maps z, the first coordinate is going by f, and the second coordinate is going by g. So if you want the first coordinate to end up in u, that's the pullback of f, and if you want the second coordinate to end up in here, it's the pullback of g. So H inverse of this is equal to that. Now, f inverse of u is open. This is open because f is a continuous mapping. This is an open set, so f inverse of that, this is going to be open, and v is an open subset of y, so g inverse of v, that's going to be open. So then this is the intersection of two open sets. It's the intersection of two open sets, and therefore that means that it's going to be open in Z. So it's going to be open in Z. So that shows that the product exists. So the product exists, and so this mapping H, there's a unique mapping to the Cartesian product, and it's continuous, and it makes the diagram commute. And now the follow-up question, so the product space exists. So why is it unique? So here's the question. So the other remaining question is, so let me take this down. It's going to get in the way. So the other question is, suppose P1 and P2 are product spaces for X and Y. We need to show that P1 is homeomorphic to P2. So so there's like two parts in that definition. We're claiming that the product space exists, which we've just shown, so such an object exists. And then we want to show that there's only one such topological space that does it for you. Any other space would be homeomorphic to it. So in the sense of topology, there's only one such space, which will be a product of X and Y. So how does one therefore do this? So this is actually going to be a very nice proof. You're going to see no set theory is going to be used here whatsoever. This is like ultra modern. So here's how it goes. We have X, so P1 is a product. So there's a pair of maps to X to Y. You can call them projection maps, but I'm just going to draw arrows. And P2 is also a product. So there's a pair of maps. Now, because P1 is the optimal, it's the optimal such product. And this is another, here you're just thinking of it as any other space with a pair of maps. The optimal property, or the universal property, says that there is a mapping, a unique mapping from here to here. Let's call it F21. It goes from P2 to P1, and it makes the diagram commute. But we can also do this the other way around. We can say P2, there's a mapping from P2 to X and Y, and also there's a mapping from P1 to X and Y. And now if we look at P2 as the optimal such product, as the optimal such space, then there's a mapping going from P1 to P2. Let's call it F12. Okay, now look at this. This part's going to be quite interesting. We go from P1 to P2, and then from P2, we can go back to P1. So we're going to draw another one going to P1. So as I said, this is very abstract. We're not using any set theory at all. We're just working on the level of mappings. This is what I find really elegant about this. So this is F21. Okay, so we can go from P1 to P2. So we can go from P1 to P2 like this. And now we have a mapping going from P1 to P2. And that's the composition, right? That's the composition. So this is going to be F12 composed F21. And now let's draw one more picture. P1 goes to X and to Y, and then we can repeat it with P1 again. Now by the universal property of P1, there's a unique map from whatever that space is to P1. But you can see what that is. In this case, it's both P1. So that has to be the identity. That has to be the identity mapping. So if you look at this picture, the mapping from P1 to P1, it has to be the identity. The only mapping from P1 to P1 that will make this diagram commute is the identity mapping, because it's unique. The identity mapping works, and because it is unique, that is the only such mapping. So whatever that is, that has to be the identity mapping. So F12 composed with F21 has to be the identity mapping, and then you can just repeat the argument the other way around. That if you do it the other way around, that's the identity. So this is the identity on P1, and that's the identity on P2. So F12 and F21 are inverse. They're inverse functions. Inverse functions. So they're inverse functions, and so P1 and P2 are homeomorphic. So your function has an inverse. So your function. So these two spaces are homeomorphic. They're homeomorphic, and you know, they're inverse functions because, you know, when you compose them in both orders, you get the identity on each of those. So they're continuous. We know they're continuous, and they're inverse functions, and all of that. So you've just proven that P1 and P2 are homeomorphic. So in a very amazing way, you've proven, this is like ultra modern, you've proven that P1 and P2 are homeomorphic spaces, and so this defines the product. This is what you call the product space on P1 and P2. So I'm sorry, this is the product space on X and Y. So the product exists, and it is unique in the sense of topology. It exists, and it is unique. When you look at this, if you've never seen anything like this before, and I imagine you probably never have, you might find this very confusing. You might say, I prefer to think of it the classical way, where you're thinking of Cartesian products and pairs of elements and all of that, and that's perfectly fine. But sometimes in mathematics, the constructions get very complicated. At some point, you'll see something called the tensor product if you've never seen it. And sometimes these constructions become very complicated. You have a product of things, and then you have a tensor product of other things within it, and then you have to take the quotient by something else, and then afterwards you have to take this thing called like the projective limit or whatever that is. And when you're trying to think on the level of sets, it becomes extremely confusing, because as a set object, the set object consists of an infinite pair of sets, and those sets are infinite pairs of other sets, and then those sets are equivalence classes of other sets. So if you think of it on the level of sets, it starts to become very confusing. And so it's a lot more convenient to focus on what truly matters. And what truly matters are the mapping properties of these spaces. That's the thing that's a lot more important than what it is as a set. So there's nothing wrong with thinking about sets. If you're comfortable doing the homework problems thinking of sets, that's fine. In fact, most problems are probably intended to be done that way. But this is, I think, a nice opportunity to introduce what is known as a universal property of an object. And you see, this is nice. So let me show you what the advantage is. So if you think of X times Y as a type of set, plus extra structure of a topology, then if you, let's say, have R2 times R3, that's not equal to R5. I mean, you want to say it's equal to R5, but it's not equal to R5, because technically this is like A and B, and technically this is like C, D, and E, and this one is a collection of 5 numbers. So technically they're not equal to each other. You see that they're technically not equal. So what you could say is, you could say there's a homeomorphism from the Cartesian product to there, where you sort of remove the extra bracket. So you can kind of do that, but you can kind of see the annoyances. You want to say it's this. You do not want to think of it like that. But that's what happens. So, however, if you think in terms of products, then you can say, right? You can say that you can say this, R is equal to R2 times R5, and here you're thinking of this equal, you're thinking of the product more abstractly. So the way you would interpret this equal to sign is you would say that R5 satisfies the criterion of the product space. So what's the criterion of the product space? The criterion of the product space would be that there's a way to map, so there's a pair of maps from R5 to R2 and R3 where you're just dropping coordinates, right? So if you have your coordinates A, B, C, D, E, you're just dropping here the first 2 coordinates, here you're dropping the last 3 coordinates, and this mapping, it's the optimal such projection mapping. So if there's any other space Z that goes into R2 and R5, it has to uniquely factor through R5. So that's what we're saying. And then this becomes like a lot more satisfying. You do not have to think of this as some kind of set and then creating a homeomorphism from there to there. You can just say that when you say R5 is equal to that, you're saying that the space R5 satisfies the product space requirement, that it projects to R2 and R3, and it's universal in the sense that any other space that projects to R2 and R3 has to necessarily factor through R5 in a unique way. And that somehow, it kind of gives you more freedom to actually care about the space or the object in question more than what it is on the level of sets. Okay, so we have this. Now, I want to talk about, so I realize that this lecture is going a bit longer than what we would like, but that's okay. So I want to talk about more products. And that is, what if you have, let's say, n spaces? You want to talk about a product of n spaces together. How would you do this? Well, if you want to do this, so on the level of sets, you take the Cartesian product and topologize it with the basis where you have, it kind of goes the same way as before, right? You topologize it with this basis. And many of the properties that we've talked about, they come through. So if these are connected, the product is connected, and if they're compact, the product is compact, and so on. So that's okay. But what if you have infinite products? What if you have an infinite product? So if you have an infinite product, then, so you have a, this is sort of the way you would write it. What would, so you have xi, I and I. You have an infinite product. So, I mean, if you have like a countable product, then you can kind of think of it as a sequence, like a sequence. So you're just picking the nth number is the nth element. But more generally, so as a set, what is an infinite product of sets? So it's kind of, it's a bit confusing. And fortunately, it's not really going to come up in this class, so you don't have to worry about it. I just want to make a comment. And I also want to show you the big advantage about thinking of products in a this sort of abstract way, as opposed to as sets. So you're going to immediately see why thinking of it as a set becomes rather confusing. So you see, when it's this infinite sequence, the nth element is being chosen in the nth set. And when it's a product of sets, you want to say the ith element is chosen in the ith set. So really, now a sequence, it's kind of like a function, right? You're mapping the set of positive integers into, you know, that's what a sequence is. So the first number, so 1 represents the first number, 2. So it's like a function. So in general, you're going to have a function from the indexing set into the union of all of these x's. And then the requirement would be is that the ith element is chosen in the ith set. Fi is an element of xi. That's kind of what we're saying here. The third element, the third position has to be in the third set. That's kind of complicated. You can see as a set, the infinite product is all of this. And then the question starts to become is, how do you then topologize this? How would you topologize this? So maybe to keep the discussion a little bit simpler, let's say we have a countable product. So you can kind of write it out as a sequence. So then it turns out that the basis looks like this. So you would think it's just a product of open sets, but with the requirement that almost all ui are equal to xi. So almost all means all but a finite number, except a finite number. So maybe the first two can be like arbitrary open sets, but then all of the other ones have to be the entire space. And it's not clear why you want that. So this is the correct way to topologize this. You would think that the way you topologize it is by using all open sets exactly how you do it before, but that's not the correct way to topologize it. And the only way to really see why that's not the correct way is to think of the product in this more abstract kind of a manner. So if we go back to the universal definition, that what we were saying that, so you can make this into a proposition. I'm not going to prove it. It says like it requires some work, but you would say that if xi are spaces, there is a product space called P. So we're not saying what it is as a set with projection maps. Let's call it pi I, where you're mapping P onto xi. And it is universal in the sense that if you have a collection of functions from any other space into any other space into xi, then there is a unique map, let's call it G, from Z to P, such that So here's xi, here's p. So this is pi I, this is fi, there's gi, such that if you do, I'm sorry, it's just g, such that pi I composed with g is fi. So the proposition is such a product space exists, okay? And then you define the product of these using this much more abstract definition. Now, the reason why the topology is the way, like if you think of it as a Cartesian product, the reason why the topology is what it is has to do with the fact that you want these to be continuous. You want these maps to be continuous. So if those maps are continuous, then what happens? Then if you pull back an open set, so if these maps are continuous, if you pick an open set in xi and you pull it back, how would it look like? It would be of the form ui. So it would just be, I mean, it's only the ith coordinate that would be ui, and everything else would just be the original. It could be anything, and it could be anything in the other coordinates. But in the ith coordinate, it has to be y. So you can see that if you want these maps to be continuous, then the pullback of an open set has to be open. So these have to be open. So these have to be open sets. And now if you have another, and let's say you have another open set, pi I of, let's say uj, then this one's going to be like x1 times x2, and then maybe at a different position, it would have uj. But because these are open sets, if you intersect them, they have to be open. So now you intersect them, and if you intersect them, then the intersection is going to go like this. You're going to have x1 times x2, and then somewhere you're going to have ui, and then you're going to have, let's say, xi plus 1 times xi plus 2 times, and then somewhere else you're going to have uj, and then you have xj plus 1, and so on. So you can see that when you intersect them in the ith position and in the jth position, they're going to be open sets, but everywhere else, they're in the entire space. And when you work with open sets, you only intersect them finitely many times. So if you take these open sets and you do finite intersections, this is how they end up looking. So the only reason, you can see that the requirement by having these projection maps be continuous forces us to consider the basis of the topology to look like that. So it's not what you think. Now I prefer to work with the product space version like this, where you define it abstractly, and then you kind of forget about the complicated set theory about how P is being constructed. But when you are actually trying to construct P as a set with a topology to show that such a thing exists, this is sort of like the reasoning for why that's being done. Okay, so, and I want to just finish one last thing on product spaces before we talk about coproducts. But the good news is coproducts are actually very easy to say. That's not going to take, the discussion on coproducts are not going to take anywhere as long as this. So let's just mention this thing. So this is called theorem, and this is called the Tikhonov theorem. So you know it's an important theorem because it's named after someone, Tikhonov theorem. And you know it's really important theorem because there's a lot of confusion about how you spell his name. So there's like 20 different ways of spelling his name. So this is called the Tikhonov theorem, and here's what the theorem says. It says that if xi are compact spaces, then the product space is compact. So the product space P. I'm not going to write out P as a set. I'm going to define P more abstractly. It's that universal space with projection maps in the optimal. So there's this universal space P, and it's also going to be compact. You do not have to assume, you do not, by the way, you do not assume that these spaces are Hausdorff. You do not assume that. And this is hard to prove. Right? This is very hard to prove. I think this is like an entire chapter in Moncrief's. Over the years, people realized that there's fancier proofs using something called ultrafilters, but we're not going to go there. We, fortunately for us, we do not have to learn the theorem. We do not have to learn the proof of this theorem. We're not going to use this result anywhere in what we do. So because of that, we just want to mention it and then move on. Okay. And the last thing I want to talk to you about are coproducts. And I know this is going much longer than what we wanted to, but at least coproducts is not going to take a lot of time. So coproducts of topological spaces. And I want to start with this. So let's start with the abstract definition first. And then I'm going to show you a set theoretic definition. So this is going to be coproducts. Now notice the word co and notice the word product. coproduct. So it's kind of like products, but whenever you see the word co in mathematics, it means the arrows, the mapping arrows, are going in the opposite direction. So here is definition plus proposition. So there's two things happening at once. We're going to define something, but the definition depends on a certain fact. So these kind of two things go together. So let X and Y be spaces. The coproduct of X and Y is another space. Let's call it C for coproduct, such that there are maps, of course, continuous maps. Let's call this IX. So I for inclusion. You'll see the reason for this later on, but it does not matter what you call these maps. I'm calling them I for inclusion because when we actually construct it as a set, you will see that these are inclusion maps. But here it's just a name of a map. So there's this map IX. So product, so you see, you're mapping. So if this was a product, you're doing this. But with the coproduct, the arrows go in the opposite direction. Coproduct. So here it's going to go like this. You're mapping X into C, and you're mapping Y into C. And this is universal. This is the optimal way to do that. This is universal. In other words, i.e., if there is another space, so if there is another space, let's call it Z, and a pair of maps, of course, continuous maps. Sometimes mathematicians get sloppy in topology, lazy, and they stop saying continuous. They just understand everything's continuous because it's topology. And there's, let's say, a pair of maps. Let's call them F from Z into C, and G from Z into C. And let's draw a picture so we see what's going on. Okay, so here's the picture. Here's X, here's Y. They're being mapped into C. This is IX, this is IY. And then we have another space over here, Z, and now the arrows go in the opposite way. This is F, and this is G. So then, and a pair of maps. So then there exists a unique continuous map. It's called H, and you have to figure out which way it goes. So I like to think of the supremum. I think of the C as the supremum of X and Y. It's like X and Y. It's like bigger than those two. They're both going into it. This is sort of like the supremum, the least upper bound, and Z is another upper bound. But C is the least upper bound, so it has to be smaller than Z. So this way, it has to go like this. Right? It has to go like this. So in the other one, it went like this. Here it goes like this. So there's a map called H. So there's a unique map H from C into Z, so that the diagram commutes. So that the diagram, I'll just say it like this, so that the diagram commutes. That means that if you go along this red arrow, that's the same thing as going IX and H, and then going F. So that's called the coproduct. The main reason why I'm introducing the coproduct, it's not really that important in topology. I mean, occasionally it comes up. It's not that important. The product is a lot more important. But because later on we'll be talking about coproducts and products involving group theory, and if you learn this, it'll make group theory substantially easier. So it's an excellent opportunity to introduce it right now. Okay, so the definition is, of course, is on this coproduct. This is the way the coproduct is defined. It's defined in a very abstract way through a bunch of mapping properties. And the proposition, of course, says that such a thing exists. Right? So the proposition is the coproduct exists. The coproduct exists. So I'm going to give you an outline of why the coproduct exists, and then you can prove it on the homework. They'll make a good homework problem to actually carefully verify these mapping properties to see that they work. So here's the way you do it. So proof that coproduct exists. So it exists for any two spaces. You can always do it. So the coproduct exists. So here's the way you do it. So we're going to assume X and Y are disjoint as sets. They're disjoint as sets. Now X and Y are topological spaces. And if you want to think of math more in a more sophisticated way, you do not care what x and y are as sets. You care a lot more about their properties. And the way you can study the property of an object is by studying how it maps into things and how it maps out of things. You do not really care so much about what it is as a set. But because we're trying to construct it as a topological space, and the way we defined topology is in terms of sets, it therefore makes sense to define it as a set. So here's the way we do it. So assume these two sets are disjoint. So we're going to set C is equal to X union Y. And this is why you want them to be disjoint. Because, well, maybe I should just say how to do it. So set C is equal to the union. And now we topologize C as follows. So this is the way we do it. So we have to say what the topological basis is. So, well, I mean, here the topological basis is going to be very simple. So we're going to, so the topological basis for C is going to be this. So it's going to consist of the following sets. U, so that U is a subset of X and it's open, and then union, let's say V. V is an open subset of Y. And in fact, yeah, so that would be your topological basis. So you pick, so if you have a subset of X, it's going to be open in the union. If you have a subset of Y, it's going to be open in the union. And then of course, what can happen is, if you take the union of a set here and a set there, it has to be also open in the union. So that's what it is as a topological space. Okay, so and then from here it's easy to see how the inclusion maps are being defined, because you're using the union. So this is just the inclusion. So this is just the map that sends X to itself. This is basically like the identity map. You're just sending X into itself because this already contains X. So it's just a pair of inclusion maps in there. So that's how you topologize C. Now the reason why it's important that they are disjoint. So here's the reason why it's important that it's disjoint. Because if they overlap, so here would be the problem. If X and Y overlap, and you pick an open subset of X, right, and you pick this open subset of X, it may not be an open subset of Y. And there's some confusion. If you pick this, if it's in the intersection of these two, is that set, are you treating that set as an open subset of X, or are you treating that set as an open subset of Y? The point is, X and Y can have very different topologies. This can be discrete, that can be indiscrete. They can be radically opposite of each other. So it becomes unclear what topology you have to use. So if X and Y are disjoint as sets, then you define C like this. Okay, and then you can topologize it in that way, and you can check that this forms a topological basis, and then you could put a topology on C. So now the union is topologized, and then you can check that this satisfies the requirement for the coproduct. Okay, and like it's almost as if you want to take their union, but the problem is X and Y are not necessarily subspaces of a larger space. You see, that's what it is. It's like the coproduct would be the union, but the problem is X and Y are not necessarily subspaces of something larger. There is no ambient space on them. So therefore, this you have to do something else. And now, what if they're not disjoint? Okay, what if X and Y are not disjoint? So you're going to do something very simple. You replace X by X prime and Y by Y prime, so that X is homeomorphic to X prime. This is the notation that is used. And Y is homeomorphic with Y prime. And X prime and Y prime are disjoint. And then the coproduct would just be their union as before. So how do you create X prime? Well, it's very simple. So here's the way you can create X prime. You can define X prime to just be X times, make up any number you want. Let's say 0. And then Y prime would be Y times 1. So by adding this extra coordinate, now you can sort of distinguish them from one another. right? An element in here will never be an element there because the second coordinates are now different. So and then you just topologize them, right? So there's a bijection between x and x prime, and then you put a topology on x prime by using the topology on x. The notation that we use for the coproduct is, if you take the coproduct, you use this notation. This is called the disjoint union. So sometimes people call this the disjoint union of two topological spaces, because you want to take their union, but they might overlap. So you have to do it in a disjoint way so that they do not overlap. And just to show a very easy example right before we go, here's an example, very silly example. What is R disjoint union R? Well, you draw the real line, okay? And then you're going to draw another real line. So this is just two parallel lines. That's what that is. It's just two parallel lines. It's just R, R, and you do it in a way so they do not overlap. So if you want to visualize it, it's just two parallel lines. So now this is connected, but the disjoint union clearly is not going to be connected. So I think that's way too much for one lecture. Feel free to rewatch parts of it.